So you did your physics lab, and now we need to analyze the data and calculate uncertainties. So to get to the point, all you need to know is shown here in this box, and I'm going to explain this very briefly, and then we'll go into some examples. So usually you have two measurements, let's say measurement A and B, and each one of them has an uncertainty, delta A and delta B. And what we need to find is value S, which is somehow related to A and B, and propagate its uncertainty. So now the uncertainty propagation will depend on how the value S depends on A and B. So first case is when S is equal to sum of A and B or difference between A and B. And then you can easily find the uncertainty S by taking square root of the squares of uncertainties in A and B. Easy. The second case is when S equals to a product of A and B, or it's a ratio of A and B. Then we'll talk about relative uncertainty, so it's your absolute uncertainty divided by the value itself, and equals to the square root of the relative uncertainty in A squared plus a relative uncertainty in B squared. The third case is when S equals to a product of some measurement A and a constant C. And it's very easy because a constant doesn't have an error. So then your absolute error in S just equals to a product of the constant itself with the absolute error of A. And the last case here is when S equals to our measurement A to some power n. Then again, we'll talk in terms of relative errors, and the relative error in S equals to the power, absolute value of power, multiplied by the relative error in A. So if this is clear, you can just take all these equations and go do your lab report. If you still have some questions, I'm going to do some examples right now. In this example, we're going to find the distance between the blue and the red flower, and we'll propagate an uncertainty in this distance. And first, we'll measure a position of each flower with respect to the edge of the stump, and we will use a ruler for that. So first, we'll align the zero of the ruler with the edge of the stump, and we'll measure the position of the first flower, which turns out to be about 4.5 centimeters, and position of the second flower is about 9.5 centimeters. So how do we know the uncertainty in our measurements? You can see that I can't really tell exactly what the position of each flower is, and it's determined by the precision of my measuring device. And in this case, since we were using the ruler, as an uncertainty, we can use the smallest increment on the ruler, which is 1 millimeter. So that's what we're going to use in this case. So each of this measurement has an uncertainty of 1 millimeter or 0.1 centimeter. So now we know the positions of the flowers and their uncertainties, and we can calculate the distance between two flowers, which is very easy. Position of the second flower minus position of the first flower, and it comes out to be 5 centimeters. All right, now let's get to the exciting part, and we'll calculate the uncertainty in the distance. So since the distance is a difference between the positions, we will use the formula for calculating uncertainties for addition or subtraction. So in this case, uncertainty in the distance equal to square root of uncertainty of position number 2 squared plus uncertainty in position number 1 squared. And I'll plug in the numbers. So we get 0.1 centimeter squared plus 0.1 centimeter squared, and it equals to 0.14 centimeters. So here's your uncertainty in distance. And now we can write the answer. So our distance between the flowers equals to 5.0 plus minus zero point 0.1 centimeters. Now let's do something a little more complicated. Let's say we have this little spider going at the constant velocity from point A to point B. And what we can do, we can measure the distance between point A and point B. And we can also time our spider and see how long does it take for him to go from point A to point B. So let's say the distance which spider traveled was 12.7 plus minus zero point 0.1 centimeters. And it took him about 7 plus minus 1 seconds to reach point B. So with this information, we can calculate the velocity with which our spider travels. And the velocity equals distance divided by time. So we have 12.7 centimeters. I'm going to carry my units with me. Divided by 7 seconds. And I get 1.81 centimeters per second. So now I can calculate uncertainty in velocity. And since velocity is a ratio of the distance and time, we will use the equation for division and multiplication to find our uncertainty. So first, we're going to talk about relative uncertainty. So delta V over V equals square root delta D over D squared plus delta T over T squared. And now I can plug in my numbers. So uncertainty in distance is 0.1 centimeter divided by 12.7 centimeters. And you can see that I have centimeters in numerator and denominator. So this value is unitless. And that's what I want because this is a relative uncertainty. And we'll do the same for time. It's 1 second divided by 7 seconds square root. And I get 0.143. And this value is unitless. So now what we want to find is absolute uncertainty in velocity. And the absolute uncertainty in velocity will have the same units as our value, so as our velocity. So for that, we'll multiply our relative uncertainty by velocity. So the relative uncertainty is 0.143, and we'll multiply it by the value which we found before, 1.81 centimeters per second, and I'm getting 0.259 centimeters per second. So now I can write the final result, and my velocity equals to 1.8 plus minus 0.3 centimeters per second. All right, now let's go crazy and do another example. Example 3. In this example, we're going to calculate kinetic energy of a moving object and its uncertainty. So we know that kinetic energy is a mass times v squared over 2. And let's say we measured the mass of our object and it came out to be 5.2 plus minus 0.2 kilograms. And this uncertainty comes from a scale you were using to measure the mass. And let's say we know that this object is moving with a velocity of 3.7 plus minus 0.3 meters per second. Now first we'll calculate the energy, which is pretty straightforward. We're just going to plug in the numbers. So 5.2 kilograms times velocity squared 3.7 meters per second squared divided by 2. You can see I'm carrying out all my units just in case. And my energy is 35.6 joules. So now the uncertainty here is going to be a little tricky. And I'm going to write out my equation for the energy like this. It's 1/2 times m and times v squared. So you can see that in front here we have a constant which doesn't have an error, and we know uncertainty in the mass of your object, but we don't know uncertainty in velocity squared, and that's what we're going to calculate first. So I'm going to bring up my cheat sheet, and you can see that this time we will be using this formula at the bottom, which allows us to calculate an uncertainty of our measurement squared. So uncertainty of v squared over v squared equals to, I'm bringing down 2 because this is a second power of velocity, 2 times the relative error in velocity. I can simplify this equation and find the uncertainty in velocity squared right away. I'm going to multiply by both sides by v squared. So the absolute uncertainty in v squared will be equal to 2 times v squared delta v over v, or simply 2v delta v. And now I can plug in my numbers. So 2 times the velocity, which is 3.7 meters per second, and multiplied by the uncertainty of the velocity, which is 0.3 meters per second, and I get 2.2 meters per second squared. And you can see that the units match. Velocity squared has units of meters per second squared. So now we know uncertainty of v squared. Let's now find the uncertainty of this product of m and v squared. And we're going to be using this second equation from our box. Uncertainty of m times v squared over m times v squared equals to square root of error in mass divided by mass squared plus error in v squared divided by v squared. And now I can go ahead and plug in my numbers. So 0.2 kilograms divided by 5.2 kilograms squared plus delta v squared I calculated, and this is 2.2 meters per second squared. And at the bottom, I will have velocity squared, and 3.7 times 3.7 is 1369 meters per second squared. This whole thing squared and square root. And the answer is 0.165. And this value is unitless because we have relative error. So now we can find absolute error in am times v squared, which equals to m multiplied by v squared multiplied by our result 0.165, and equals to 11.746 kilograms meter squared per second squared. So now the last step which I need to do is to find uncertainty of a product between mv squared and this constant, and we're going to be using this equation number 3, and it's very easy because absolute uncertainty will be just equal to the constant multiply by the absolute error of mv squared. So we can write down that delta E equals uncertainty of 1/2 times mv squared, and I can pull out 1/2, and then I can plug in my numbers. 1/2 times 11.746 kilograms meter square per second squared, and I get 5.87 joule. That's it. Now I can write my answer and round up my errors, and I get 35.6 plus minus 5.9 joules. Boom. And that's how you do error propagation. Now you can go and do your lab report.